motor is different from that required for an application, speed reducers, frequently called gearboxes or gear reducers, are often used to lower the speed. Usually the reducer or gearbox consists of a set of gears enclosed in a sturdy metal housing. The housing keeps the gear set aligned so the gear teeth mesh correctly. Correct alignment increases the life of the gearing and transmits power efficiently. The power typically comes from a motor or other driver which is coupled to the input shaft. The speed and power of the motor are transmitted through the gearing to the output shaft, either by complete reduction, in which the reducer is connected directly to the driven machine, like this, or by partial reduction, like this belt drive that further adjusts the speed. Now, most reducers are basically the same, so once you know how to maintain and troubleshoot one, you'll be able to do a pretty good job with all the others you might have to work on. In this program, we'll show you the basic parts of all reducers. We'll show you some of the common things that go wrong with them. We'll show you how to spot problems early, before they become serious. We'll show you how to maximize the efficiency of the reducer and extend its life. And we'll show you what to look for during an overhaul. Let's start with the basic parts of a common gear reducer. Here's one of the most common types, a worm gear reducer. We already mentioned the input and output shafts. These can really stick out just about anywhere, depending on the design of the reducer, what kind of gears are in it, and the application. In terms of the input and output shaft, there are really just three kinds of reducers. The concentric or inline reducer, in which the input and output shafts are directly in line with each other, like this. The parallel or offset shaft reducer, in which the shafts are mounted at opposite ends of the reducer. And various kinds of angle shaft reducers, like the worm reducer. However, reducers are also classified by their gear trains: single reduction, double reduction, triple reduction, and so on. In a single reduction unit, a gear on the input shaft drives a gear on the output shaft. In other reducers, the input shaft drives an intermediate gear, which may drive another intermediate gear, or the output shaft. Anything beyond a triple reduction is relatively uncommon. Let's get back to the worm reducer. Here, the shaft of the worm is coupled to the shaft of the driver. Typically, this is done with splines on the shaft like this, or with a key and keyway like this, and sometimes with a coupling. When the worm turns, its teeth rotate the gear wheel fastened to the output shaft. Since this wheel is a good deal larger, its shaft rotates more slowly, usually a lot more slowly. Worm reducers are often used when there is a need to greatly reduce shaft speed. Typical input to output speed ratios on a worm reducer are at least 20 to 1 and may go as high as 3,600 to 1 or more. This means that 3,600 turns of the input shaft will turn the output shaft around just once. Of course, different reducers will have different ratios. Many reducers are custom assembled by a manufacturer or distributor from in-stock parts to match the requirements of a particular application. Swapping out the gearing changes both speed and torque at the output shaft. Handling the high speeds and torques requires firm shaft support as well as precision shaft alignment. Support is provided by the reducer housing, usually made of cast iron or fabricated steel, and by bearings set into the housing. Input shafts of smaller reducers are sometimes supported by ball bearings, often a bearing at each end of the shaft, but sometimes just a single bearing. Output shafts are usually supported by roller bearings. Almost always there are two bearings, one at either end of the shaft. This provides greater support for the load. Realignment of shafts within a reducer is normally done only if the reducer has been mechanically damaged, if it has been run hot enough to burn up the lubricant and seals, or if it is being overhauled and the shafts, bearings, and gears are being removed for repair or replacement. However, the alignment of the input shaft with the driver and the alignment of the output shaft with the driven machine is critical. Misalignment will put excess load on the bearings, wearing them out much more quickly. Misalignment will increase the damage caused by shock loading, and misalignment will wear out seals rapidly, allowing lubricant to leak out and contaminants to leak in. But if a reducer is properly sized for its application, if it is correctly aligned, and if shock loading is kept to a minimum, then failure will almost always be the result of lubricant failure. The lubricant got too hot, it was contaminated, or a seal leaked and lubricant levels were too low for too long. We'll get to sizing a reducer for its load in a few minutes, but first, let's have a look at lubricants and seals. Wherever a shaft penetrates the casing, a seal will be required. The seal has two purposes: to keep the lubricant in and to keep contaminants out. All seals will eventually fail, but seals that are correctly installed and properly maintained will maximize machine efficiency and minimize downtime. The basic type of seal used in most reducers is a dual-lip, full-ring contact seal in a seal case. The inside lip of a seal usually has a small spring, a garter spring, which keeps the lip in contact with the shaft. The outer lip's resiliency keeps it in contact with the shaft. Some manufacturers also include other assemblies, like this outer seal, which can be filled with grease to block contaminants from getting to the inner seal. The seal is often held in place by a retainer. Now, sometimes just the seals on a reducer are replaced, and the reducer doesn't have to be opened up. Let's see how that's done. Now, the first step when doing any maintenance on a reducer is to lock it out. Follow the established lockout procedures for the facility in which you work and for the particular piece of equipment you'll work on. After the machine is properly locked out, start by cleaning off the shaft and the outside of the reducer around the seal. This will help keep contaminants out of the reducer when the old seal is removed. Next, remove the seal cage assembly. Most seals have gaskets, and these will have to be replaced with new ones. Check the manufacturer's specifications to make sure you know which ones to use. They will have to be the same size and shape, and they will have to be of a specific thickness as well. Work carefully. If the seal cage is damaged in the process, it will have to be replaced. Do not attempt to reuse a seal cage that is bent, distorted, or scored, because the seal will probably leak. Clean the seal cage thoroughly and remove any gasketing material. Some manufacturers specify a sealing compound for coating the seal prior to installation. Follow the manufacturer's instructions, then place the seal squarely in the seal cage with the garter spring on the side of the cage that will be toward the bearing. Press or tap the seal into place by using a cylindrical tool that applies pressure evenly around the circumference of the seal case. Pressing or tapping directly on any small portion of the seal case will distort it, damaging the seal and almost certainly causing a leak once it is reinstalled. Before installing the seal cage and seal, be sure to clean off the shaft and clean off the face of the reducer. When cleaning the shaft, do not scrape or use abrasive materials on the part of the shaft that has been polished by the seal. This polished section will be bounded on either side by seal paths or wear tracks. They should be very narrow, generally no more than 2/100ths of an inch, and barely felt when passing a fingernail over them. Paths that are significantly wider or deeper indicate shaft misalignment, cocked seals, or a shaft that does not run true. Failure to correct any of these conditions and failure to repair the shaft will probably result in leaks when the new seal is installed. When cleaning off the face of the reducer, be sure to scrape off any old gasketing and clean the surface thoroughly. The condition of the surface and the thickness of any gaskets or any shims may be critical to the proper operation of the reducer. In some cases, especially when replacing seals at the output shaft, you may have to measure and set the axial float on the shaft as well as set the preload on the bearings. Axial float is a measure of how much the shaft will move back and forth. Typically, this is just a few thousandths of an inch. Depending on the manufacturer, it may have to be set to within a thousandth of an inch or less. A dial indicator is normally required to measure axial float accurately. Be sure to follow the procedures and specifications set forth by the manufacturer. Preload refers to the load placed on the bearings before any running load is added. Usually, preload is set indirectly by measuring the axial float, then varying the thickness of the gaskets and shims. Again, preloads are often set to within a thousandth of an inch or less, so a dial indicator and a copy of the manufacturer's service manual are normally required. When installing gaskets, always use new ones. In many cases, the gaskets also serve as shims, shim gaskets as they are called. They are designed to compress a specific amount when installed. Because used gaskets or shim gaskets have already been compressed, they may not provide the correct axial float, the correct preloading, or the correct alignment. With the required gasketing and shims in place, the new seal can be installed. Damage to new seals occurs most often as they are being slid over the shaft. To help prevent this, cover the shaft with thin, tough paper or plastic, then lubricate both the covering and the seal. When sliding the seal into place, be careful not to cut the seal or expand it. Do not unseat or damage the garter spring, and do not distort the seal case. Any of these can result in a seal that leaks either at startup or soon afterward. In many cases, the seal cage must be centered on the shaft, but be sure to consult the manufacturer's instructions because there may be registration marks that need to be lined up. As we said before, the seal keeps lubricant in the reducer, but we also said that every seal eventually fails, so every reducer eventually leaks. As that happens, lubricant levels gradually drop, and the remaining lubricant heats up and can oxidize very quickly. When this happens, bearings begin grinding and can break down quickly. And seals can become as brittle as plastic within minutes if temperatures are high enough. Many reducers have a sump from which the lubricant circulates through the reducer. Sometimes this is done by the action of the gearing, as in this small worm reducer. But other reducers may have splash oilers, oil slingers, or other oil distribution systems. These may include pressurized oil delivery systems that pump the lubricant where it is needed. Oil pumps are often used when input or output shafts are oriented vertically. Many larger reducers include oil filters, and most have air breathers to equalize pressure and help assure oil flow. Adequate lubrication is so important that most facilities have a routine program for checking lubricant levels. Many larger reducers have automotive-type dipsticks, while others have sight gauges or other oil level indicators. Smaller reducers may have an access plate or plug to check lubricant levels. If lubricant has become contaminated by dirt, grit, grime, or water, it will quickly destroy bearings and gears. The source of the contaminant should be identified and eliminated, and the lubricant should be changed. All air breathers should be checked and kept clean. Reducers that run too hot will break down more often because high temperatures degrade both the seals and the lubricant itself. Most lubricants used in reducers oxidize very rapidly above 200 degrees. Speaking roughly, seal life is halved for every 50-degree rise in temperature above 200 degrees and doubled for every 25-degree temperature drop below 200 degrees. To extend the life of the lubricant and the seals, some reducers include a fan to help move cooler air across the radiant surface of the reducer housing. Usually, the more efficiently the reducer converts input power into output power, the less likely it is to have a fan. Many reducers have fins to help remove heat. Finally, be sure to check for leaks. All seals leak a little, sometimes as much as a drop or two a day, even when new. In general, a seal that leaks as much as half a dozen drops per hour should be replaced. Leaking oil not only creates a housekeeping problem, but it can be a fire hazard as well. Okay, now we've seen the major components that all reducers have in common. We've looked at the input and output shafts, at the bearings, at how to replace a seal, and we've seen the importance of lubrication and simple maintenance routines in making sure a reducer operates reliably and efficiently. Now let's look at some non-routine maintenance, an overhaul. And while we're at it, we'll look at the main components of every reducer, the gearing. As we said before, the speed and power of the motor are transmitted through the gearing to the output shaft. The type of gearing in the reducer has a lot to do with how much power is transmitted. In all cases, of course, the reducer and its gearing must be matched to the application if long, reliable service is expected. Reducers are selected for an application based first on the gear ratio. The speed of the driver is compared to the desired speed of the output shaft to determine the gear ratio required. For example, if the input speed of the driver is 3,600 RPM and the desired output is 100 RPM, then the gear ratio is 3600 divided by 100, or 36 to 1. In practice, manufacturers generally make standard ratios like 5 to 1, 15 to 1, 40 to 1, and so on, so the output speeds for any prime mover driving through a reducer are often decimal numbers, like 58.33 RPM for a 30 to 1 reducer operated by a 1750 RPM driver. After the correct ratio is chosen, reducers are generally sized by two factors. The first is a mechanical rating, usually expressed as the power a unit can transmit. In addition, it will have a thermal rating, which specifies the power a reducer can transmit without exceeding the manufacturer's recommended temperature rise. Thermal rating should always be considered carefully because, as we have seen, long-term reliable operation depends on heat and the effect of heat on seals and on lubricants. Most reducers also have three other important ratings. One rating is a service factor. The service factor is easier to understand if you think of it as applying to the application rather than to the reducer. In fact, to get the service factor, you'll refer to a list of applications, like this one published by AGMA, the American Gear Manufacturers Association, and in common use by most manufacturers. The charts are based on three factors: the type of load, the duty cycle, and the type of prime mover. For example, a hammer mill is in a heavy shock load class, and when operated 24 hours per day by an electric motor, it would have a service factor of 2.0. Operation for up to 10 hours per day would reduce the service factor to 1.75. Operation for 3 hours per day would reduce the service factor to 1.5. And operation for only a half hour per day could reduce the service factor to 1.25. Operation of the hammer mill by a multi-cylinder internal combustion engine, however, would change each of these service factors. The service factor is used to select an appropriate reducer. For example, if an application has 20 horsepower load with a service factor of 1.5, the reducer selected must be capable of delivering 30 horsepower without exceeding its thermal rating. Another rating is the overload capacity. Typically, this will be 200% of the power rating. This means, for example, that the reducer can handle a temporary overload twice as large as its rating. The overload, however, must be applied only intermittently. Usually, this means no more than a few times during any 10 hours of operation. The third rating is the maximum overhung load. This refers to how much weight the input and output shafts must carry as a result of the driver and the driven load. Exceeding the maximum overhung capacity will damage the reducer. Usually, it's not difficult to spot a misapplied reducer. It'll run hot. Its lubricant will require frequent replenishment and frequent changing. Seals and bearings will wear out quickly. And the gear teeth will probably be damaged. A close examination of the gear teeth can tell you a lot. The most common problems are pitting of the tooth surface and fatigue cracks at the root of the gear teeth. Gears are rated based on how badly they pit and how easily they crack. If the reducer is not being opened up for an overhaul, castings or prints of the teeth can sometimes be made. An analysis of these prints can often pinpoint operating problems long before they become serious. Of course, if you're overhauling a reducer, you'll be able to take a good close look at all the gears. Some types of wear obviously mean trouble. These teeth were badly bent, and some even stripped off. The gearbox was seriously overloaded, far in excess of its rating. However, problems like this are usually preceded by signs of failure. When gearing is greatly overloaded, or when it is repeatedly overloaded to a lesser extent, it will often develop cracks at the base of the teeth. In general, you can expect that the life of a gear will be reduced by a factor of 8 if the full load is doubled. This means gearing that might have run reliably for 25,000 hours may break down in about 3,000 hours. Now, not all obvious wear is bad. There is a kind of normal wear that occurs when gears are operated at or near full load. The pattern of wear appears in the dedendum, below the midpoint of the tooth. It's called pitting, and it looks like a lot of small pits or holes in the surface of the tooth. If the pits remain shallow, and if they are all in the dedendum, and if the edges of the pits gradually wear down, then this kind of wear is considered normal. However, if the pits get deeper, or if the pitting extends beyond the dedendum, or if the edges of the pits do not wear down, then destructive pitting is occurring. The gear is on its way to failure, usually fairly quickly. Many other kinds of wear can occur, and all of them can tell you a lot about what's going on in the reducer. When overhauling a reducer, it is often worthwhile to compare gearing with descriptions of known kinds of wear to determine what may be going wrong. Standard descriptions and photographs of common wear patterns are available from many manufacturers and from AGMA. Now, before you start removing a reducer for an overhaul, there's always one thing to do first: lock it out. As we said before, follow the established lockout procedures for the facility in which you work and for the particular piece of equipment you'll work on. The next thing to do is make sure you keep the manufacturer's service manual handy. Do not attempt to overhaul a reducer without it. Very often, specific sequences must be followed during disassembly and during reassembly in order to prevent component damage and to assure correct operation. Start by cleaning off the reducer as best you can. The cleaner it is before you break loose any bolts, the less chance there will be to get dirt and grime in the housing, on the gearing, and in the bearings. On small reducers, you'll want to drain the oil first before disassembling the housing. On larger reducers, the cover can usually be removed first. Be sure to consult the manufacturer's service manual for the proper procedures about how this is done. For example, some reducers have dowels that must be removed, while others do not. Some bolts should never be removed, or only loosened, while others must be removed entirely. On some reducers, bolts below the housing split should be loosened but left in place. It's good practice to wire shims and shim gaskets in place to keep track of them for later replacement. In most reducers, the gearing and shafts must be removed in a specific order. The high-speed input shaft and gearing, then the intermediate gears, if it is a multiple reduction unit, then the low-speed output shaft and gearing. It is critical to hoist the gearing straight up. Gear teeth are easily damaged if they bump against each other. Normally, you'll replace all the seals, and you'll replace all the bearings for the shafts that have been removed. Use the correct tools when working with bearings: a bearing puller to remove them, a controlled heat source to expand the new replacements. Clean the air breather, and clean or replace the filter if there is one. Clean the inside of the housing thoroughly, and clean the oil pans, troughs, and any other lubricant distribution systems. Use approved solvents. Carefully examine the shafts and gearing for signs of damage. Damage to the gear teeth other than normal pitting usually calls for replacement of the gear. In some cases, this will mean replacement of the shaft as well, because some gears, especially small pinion gears on a high-speed shaft, cannot be removed without destroying them. Check the shafts, especially for seal wear paths that are too wide or too deep. This is a common cause of leaking seals. Shafts with pronounced wear paths should be resurfaced or replaced. Sometimes, shafts can be adjusted during reinstallation so that the seal rides on a new section of the shaft. When reassembling a reducer's gearings, shafts, and the housing, be sure to follow the manufacturer's specifications for correct tightening. Failure to achieve the proper torque for lock nuts and cover bolts, or to follow other instructions for tightening, could result in serious damage to the reducer during operation. Use a properly calibrated torque wrench and an impact wrench if required. During reassembly, be sure to read and follow the manufacturer's instructions carefully. Often the axial float of bearings will have to be set, typically to within a couple thousandths of an inch. All shim gaskets and gaskets should be replaced. Reassembly should be done in the reverse order. Generally, the low-speed output gearing and shaft, followed by any intermediate gearing, and finally, the high-speed input gearing and shaft. Do not bump the gears together. Again, refer to the manufacturer's service manual. If shafts are being reversed or replaced or offset, you may have to switch oil pans and troughs around, or you may have to rewire the motor. Finally, add the cover gasket if there is one, or coat the top of the base split with a sealant. Then lower the cover into place and tighten all bolts to the specified torque. Recheck the axial float of each shaft. Turn the gear train by hand. Then add lubricant to specifications. Overhauled reducers should run without a load for an extended period of time. while temperature and oil levels are checked periodically. In this program, we've shown you the basic parts that all reducers have in common: shafts and seals, bearings and gears. We've shown you some of the common things that go wrong with reducers and how to spot them early. If you follow the basic maintenance guidelines in this program, you'll be able to maximize the efficiency of the reducers you work with. You'll be able to get them back up and running again quickly when things do go wrong, and you'll be able to keep them working reliably for a long time.